The cosmos is a vault of unsolved riddles. What secrets does deep space hold that even our brightest minds cannot explain? We are embarking on a journey through 30 of the universe's most baffling phenomena, cosmic puzzles that challenge the very foundations of physics and reality. You will discover the forces pulling entire galaxies toward an unseen monster, and the strange signals that whisper of possibilities beyond our comprehension. By the end, you will see the night sky not as a static picture, but as a living, breathing mystery. Why does the universe appear to have a preferred direction, and what could be causing stars to flicker in ways that defy all logic? What cosmic mystery do you find most compelling? Our own galaxy is racing through the cosmos at over 1,000,000 miles per hour, pulled by a force we cannot see. This is the mystery of the Great Attractor, a colossal gravitational anomaly located in the distant Centaurus supercluster. It acts like a cosmic vacuum cleaner, drawing not just our Milky Way but countless other galaxies toward it in a river of motion that spans the universe. For decades, its true nature remained hidden from us, obscured by a cosmic curtain known as the zone of avoidance. This is the thick plane of our own galaxy, a dense band of stars, gas, and dust that blocks our view of what lies beyond, placing the Great Attractor directly in our blind spot. It is as if we are trying to see a distant city through a dense, luminous fog. To pierce this veil, scientists turn to instruments that see more than visible light. Powerful X-ray telescopes like the Chandra Observatory can peer through the cosmic dust, revealing the high-energy signatures of galaxy clusters and vast structures hidden behind the Milky Way's core. These missions are slowly mapping the unseen, suggesting the Great Attractor may not be a single, monstrous object, but perhaps an immense concentration of mass, a gravitational focal point in the cosmic web. What could possibly hold such sway over the motion of galaxies, and what will we find when we finally see what has been pulling us all along? But the Great Attractor is not the only force guiding our motion. There is something else, an even more unsettling current moving through the cosmos. Hundreds of galaxy clusters are all streaming in the same specific direction, like leaves caught in a river flowing toward a destination we cannot see. This phenomenon is called dark flow. It was discovered by peering into the faint afterglow of the Big Bang itself, the cosmic microwave background. Scientists used this ancient light as a cosmic frame of reference, a stationary backdrop against which they could measure the motion of enormous clusters of galaxies. The expectation was that these clusters would be moving randomly, their motions governed by the gravitational tugs of their local neighbors. Instead, they found a coordinated, sweeping motion on a scale that is simply staggering. These vast islands of stars and dark matter are all being pulled in a uniform direction that points far beyond the edge of our observable universe. This motion cannot be explained by any known structure, not even the immense Great Attractor. The gravitational source for this dark flow must lie outside our cosmic horizon, in a realm of space and time from which light has not yet had time to reach us. This suggests that the structure of the cosmos extends far beyond what we can ever hope to see. The observable universe, everything we know, might just be a small part of a much grander, perhaps infinite reality. One theory posits that the dark flow is caused by the gravitational pull of another universe, a separate bubble of space-time brushing against our own in the greater multiverse. How do we comprehend a force that originates from outside our reality? What colossal structure, or perhaps what other cosmos, could possibly exert such an influence over our own? While our galaxy rushes toward an unseen horizon, another mystery arrived not as a slow pull, but as a sudden, deafening shout. On a quiet August evening in 1977, the Big Ear radio telescope at Ohio State University was silently scanning the sky when it recorded something extraordinary. A narrowband radio signal bursting from the direction of the constellation Sagittarius, rose in intensity for a full 72 seconds before fading away. It was so powerful, so perfectly tuned to the hydrogen line frequency that scientists consider a likely channel for interstellar communication, that its statistical significance was off the charts. When astronomer Jerry Amon saw the data printout, he circled the string of letters and numbers and simply wrote, "Wow." That single handwritten exclamation gave the signal its famous name. The WOW signal remains one of the most tantalizing and unexplained events in the history of the search for extraterrestrial intelligence. Its characteristics pointed to a source far beyond our solar system, a beacon that seemed artificial in its precision. The hunt for a repeat began immediately. For decades, astronomers have pointed their dishes toward that same patch of sky, listening intently for another whisper, another confirmation. They have heard only silence. The absence of a repeat signal is as puzzling as the original event itself. If it was a message, why was it sent only once? Proposed explanations range from the mundane to the extraordinary. Some suggested it was a signal from a passing comet, but the comet in question was not in the right part of the sky at the time. Others point to a military transmission or a satellite reflection, yet no terrestrial source has ever been convincingly matched to that specific time, frequency, and direction. The most profound possibility that it was a one-time broadcast from an advanced civilization continues to captivate us. It was a cosmic flash in the pan, a single, brilliant note in an otherwise silent symphony. What could have caused such a perfect, powerful, and fleeting signal? Was it a malfunction in some distant probe, a celestial lighthouse sweeping its beam past Earth for just a moment, or a message we were never meant to fully understand? The WOW signal is a ghost in the machine of the cosmos, a reminder that sometimes the most profound answers come in the form of a question we cannot answer. The silence of space can be deeper than we ever thought. Beyond the faint whispers of ancient signals lies a region of almost perfect emptiness, a spherical void so immense it challenges our understanding of the cosmos itself. This is the Boötes Void, a place astronomers call the Great Nothing. Stretching an astonishing 330 million light-years across, this cosmic desert is not merely a gap between galaxies, it is a staggering absence of them. If you placed our Milky Way at the center of this void, we would not have known other galaxies existed until the 1960s. The sheer scale of this emptiness defies all standard models of how the universe is supposed to be structured. On the largest scales, matter should be distributed in a vast, frothy web, with great walls of galaxies surrounding bubble-like voids. But even the largest predicted voids are dwarfed by the Boötes Void. It is an anomaly of nothingness, a hole in the cosmic fabric that is far too big to have formed through the gentle tug of gravity alone. So what could have possibly scooped out such a colossal volume of the universe, leaving behind a near-perfect vacuum? The answer remains one of cosmology's great puzzles. Some theories suggest it is the result of a merger of smaller voids, a chance confluence of emptiness that created a supervoid. Others have proposed more exotic ideas, like the imprint of a collision with another universe in the multiverse. Yet the void is not completely barren. Scattered across this immense darkness are a few dozen incredibly isolated galaxies. These lonely islands of stars are all that remain in a space that should contain thousands. Imagine being on a planet within one of these galaxies. Your night sky would be almost perfectly black, devoid of the faint, fuzzy smudges of neighboring galaxies that dot our own sky. The cosmic web would be a distant legend with only a handful of faint stellar siblings visible in an ocean of darkness. The existence of these galaxies deepens the mystery, for they raise a haunting question. Did something catastrophic clear out this region, leaving behind these few survivors, or was the matter here simply never there to begin with? The Boötes Void stands as a monument to the unknown, a silent and profound reminder that the universe's greatest puzzles are not just about what is there, but about what is not. From the profound silence of cosmic voids, we turn our gaze to a star that refuses to be ignored. KIC 8462852, better known as Tabby's star, behaves like no other sun in our galaxy. Discovered by citizen scientists sifting through data from the Kepler Space Telescope, its light does not dip in the gentle, predictable rhythm of orbiting planets. Instead, it plunges into darkness. This star experiences dramatic, irregular dimming events, sometimes fading by a staggering 22%. A planet, even a gas giant, would block less than 1% of a star's light. What object or collection of objects could possibly obscure that much of a star's face? The hunt for an answer has captivated astronomers and the public alike. The most conventional explanation points to a vast, chaotic swarm of comets, thousands of them, surrounded by thick clouds of dust and debris. If such a family were orbiting the star in a tight, elliptical path, their collective material could potentially block the light in the bizarre patterns we observe. Yet the scale required is immense, pushing the limits of what we believe a typical comet cloud could be. Another possibility involves circumstellar dust, a thick ring of rocky debris orbiting very close to the star itself. This dust would be uneven and clumpy, causing the erratic dimming, and its proximity to the star's intense heat would explain why we do not detect the excess infrared radiation we would expect from a cooler, more distant dust cloud. Then there is the more speculative, yet utterly fascinating alien megastructure theory. The idea is that an advanced civilization, one far beyond our own, could be building a Dyson sphere, or at least the beginnings of one. This hypothetical structure would be a vast array of energy-collecting satellites encircling the star to harness its total power output. Such an incomplete, lopsided swarm would indeed cause the wild, aperiodic dimming we see. While scientists consider this the least likely scenario, its sheer audacity has fueled intense public interest and highlighted how the search for the unknown can lead us to question everything. Astronomers worldwide are now in a constant state of watchfulness. Ground-based observatories and space telescopes have joined a coordinated campaign, monitoring Tabby's star around the clock, waiting for it to dim again. Each new dip in its brightness is a potential clue, a chance to capture its spectrum and finally identify the material that is blocking the light. The mystery of Tabby's star is a reminder that sometimes the most compelling discoveries are not answers but questions. They are the anomalies that force us to look closer, to challenge our assumptions, and to wonder what incredible structures or natural phenomena might be waiting in the dark. The erratic flickering of Tabby's star pales in comparison to the raw, explosive power of another deep space anomaly. Fast radio bursts are the universe's most brilliant and fleeting flashes, releasing in a single millisecond as much energy as our sun puts out over 3 entire days. These are not gentle whispers from the cosmos. They are deafening, interstellar screams that travel for billions of light years before our telescopes catch their final, dying echo. The first one was discovered by accident in 2007, hidden in archived data from a radio telescope in Australia, and for years astronomers debated whether it was even real. Now we know they are happening all the time, all across the sky. The puzzle of fast radio bursts lies in their dual nature. Some are loners, a single, spectacular blast from the depths of space that never repeats. Others are stubbornly chatty, sending out flash after flash from the same patch of sky, allowing scientists to pinpoint their home galaxies. This fundamental difference suggests there might be multiple cosmic engines capable of producing these incredible outbursts. So what cosmic catastrophe could possibly create such a brief, yet unimaginably powerful signal? The leading suspect is a magnetar, a type of neutron star with a magnetic field so intense it could strip the information from every credit card on Earth from halfway across the galaxy. A starquake on the surface of such an object, a sudden cracking of its crust under immense strain, could release a titanic shockwave and blast a radio burst across the universe. Another compelling theory involves the violent merger of two neutron stars, a collision so energetic it warps the fabric of spacetime itself, sending out gravitational waves alongside a flash of radio light. Yet, the existence of repeaters challenges these cataclysmic models. If a merger destroys the system, how can it burst again? This has led to more exotic ideas, like the possibility of highly magnetized pulsars interacting with clouds of surrounding material, or even flares from distant active black holes. The key to solving this mystery has been a new generation of telescopes designed to catch these flashes in the act. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is a revolutionary instrument that has no moving parts. Instead of a single dish, it uses over 1,000 antennas to stare at a huge swath of sky every day. This wide-eyed view has turned it into a fast radio burst factory, detecting thousands of these events and providing the vast dataset needed to start classifying them. Each new detection is a clue, a single frame in a high-speed movie of cosmic destruction. By tracing the bursts back to their host galaxies, astronomers are learning that they come from all types of environments, from young, star-forming galaxies to old, quiet ones. This diversity hints that the recipe for a fast radio burst might not be a single, rare ingredient, but a more common process we are only beginning to understand. What does it mean that the universe is constantly flashing with these brilliant, mysterious signals? Are we listening to the death cries of stars or the birth announcements of new celestial objects? The universe screams with possibility, yet we are met with a profound and unsettling silence. This is the heart of the Fermi Paradox, a simple question with terrifying implications. If the universe is so vast and so old, with billions of planets that could support life, then where is everybody? The numbers seem to guarantee that we are not alone. Our galaxy alone contains hundreds of billions of stars, and many of these are older and more stable than our own sun. There has been more than enough time for other intelligent species to arise, to develop technology, and to spread across the stars. They should be everywhere. The fact that we see no signs of them, no grand structures, no visiting ships, and no unmistakable communications, creates a paradox that cuts to the core of our place in the cosmos. So what is the great filter that holds life back? One chilling answer is the great filter hypothesis. This idea suggests that there is at least one nearly insurmountable barrier that prevents life from progressing to the point of interstellar colonization. The terrifying part is we do not know if we have already passed through this filter, or if it still lies ahead of us. If the filter is behind us, it could be something like the transition from single-celled to complex multicellular life, which took billions of years to occur on Earth. This would mean we are rare pioneers, the first to make it this far. But if the filter is ahead of us, it could be a future catastrophe that inevitably destroys all advanced civilizations. Perhaps every technological society eventually creates its own doom through climate change, nuclear war, or a nanotechnology disaster. Or maybe they encounter something out there, a natural cosmic phenomenon like gamma-ray bursts that periodically sterilize galaxies. Another possibility is that intelligence itself is not what we think it is. What if the next step in evolution is not to build radio telescopes and rockets, but to retreat into immersive virtual realities or to transcend into a state of pure consciousness that has no need for physical exploration? Their existence would be utterly alien to us, leaving no trace we could possibly detect. Then there is the zoo hypothesis, which paints Earth as a cosmic wildlife preserve. Advanced civilizations could be aware of us but have chosen a strict policy of non-interference, observing our development from a distance to see how we evolve naturally. We might be living in a designated wilderness area, isolated for our own protection or for study. Or perhaps the answer is more bleak. Maybe the universe is simply too big and too old. Civilizations could bloom and die in the cosmic blink of an eye, their brief signals vanishing into the interstellar static before they ever overlap with another. We could be like ships passing in an endless dark ocean, forever alone not by design, but by the sheer crushing scale of time and space. The silence we hear is not an empty one. It is filled with questions about our own future. Are we on the cusp of a great awakening, or are we simply alone in a quiet, unresponsive void? The profound silence of the cosmos is matched only by the profound absence of something else, a ghost that permeates every corner of space. We know this ghost only by its shadow, a substance we call dark matter. It is the universe's greatest unsolved puzzle, an invisible form of matter that makes up roughly 27% of everything that exists. We cannot see it, touch it, or detect it with any of our instruments, yet we are certain it is there because of the way it commands the motion of galaxies with its gravitational hand. The first clue emerged from the way galaxies spin. When astronomers measured the speeds of stars orbiting within spiral galaxies, they expected the stars on the outer edges to move slower, just as Pluto orbits our Sun much more sluggishly than Mercury. The gravitational grip should weaken with distance, but that is not what they found. The stars far from the galactic center were whipping around just as fast as those near the center. It was as if the entire galaxy was embedded within an immense, invisible sphere of mass, a halo of something unseen whose gravity was holding the speeding stars in place. Without this dark anchor, these galaxies should have long ago flown apart. The evidence only grew stronger with a phenomenon called gravitational lensing. The immense gravity of a massive object like a galaxy cluster can act as a cosmic magnifying glass, bending and warping the light from more distant galaxies behind it. By studying this distortion, scientists can map the cluster's total mass. Time and again, they found that the visible mass of the stars and gas was only a small fraction of the total mass required to create such a powerful lens. The majority of the mass was missing, a clear sign of dark matter's pervasive presence. So what is it made of? The leading theory points to as yet undiscovered particles, ones that interact only feebly with normal matter, passing through our planet and our bodies as if they were not even there. Deep underground, in abandoned mines and beneath mountains, scientists have built exquisitely sensitive experiments to catch one of these phantom particles. They wait in the profound, quiet and dark, shielded from cosmic rays, hoping for a rare, telltale bump that would signal a collision with the dark world. For decades, these detectors have remained silent. This persistent lack of a direct detection has led some physicists to propose a radical alternative. Perhaps there is no dark matter at all. Maybe our understanding of gravity itself is incomplete. Modified Newtonian dynamics, or MUND, suggests that the rules of gravity change on the immense scales of galaxies, creating the illusion of extra mass without any being there. While MUND can explain some galactic rotations, it struggles to account for the bullet cluster where two galaxy clusters collided. Observations show that the dark matter, mapped through its gravitational lensing effect, sailed right through the collision, separate from the visible gas. This seems to show that dark matter is a real, physical substance that can be separated from normal matter. The question remains, are we on the verge of a monumental discovery, finally detecting a particle that makes up most of the matter in the universe, or are we chasing a ghost, destined to rewrite the fundamental laws of physics instead? Dark matter's ghostly presence is rivaled only by a force even more mysterious and dominant. Dark energy makes up a staggering 68% of the entire cosmos, a pressure woven into the fabric of space itself that is relentlessly pushing the universe apart. Its discovery at the end of the 20th century was a profound shock, completely overturning our expectations for the cosmic future. Astronomers had long assumed that the universe's expansion, a remnant of the Big Bang, was gradually slowing down over time, pulled back by the collective gravity of all matter. To test this, two independent teams set out to measure the expansion rate by observing a special kind of stellar explosion, a Type 1 supernova. These supernovae are cosmic standard candles, exploding with such a consistent, known brightness that by measuring how dim they appear from Earth, we can calculate their precise distance. By looking at incredibly distant supernovae, the teams were peering billions of years into the past. They expected to find that these ancient explosions were brighter than expected, meaning the universe was expanding more slowly back then. Instead, they found the opposite. The supernovae were fainter. This could only mean one thing: those far-off galaxies were fleeing from us faster than anyone had predicted. The expansion of the universe was not slowing down, it was accelerating. This revelation was so monumental it earned the teams the Nobel Prize in Physics in 2011. They had uncovered a force that acts as a sort of anti-gravity. Unlike gravity, which pulls things together, dark energy is a repulsive force, an inherent property of empty space that causes the cosmos to stretch at an ever-increasing rate. The leading theory describes it as the energy of the vacuum of space, a concept rooted in quantum physics where particle pairs flicker in and out of existence. Yet when physicists calculate how much energy this quantum foam should contain, the number is off by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. This colossal mismatch means we fundamentally do not understand what dark energy is. Its discovery forces us to confront the ultimate fate of the cosmos. If dark energy remains constant, the acceleration will continue forever. Galaxies will be pulled so far apart that the space between them will expand faster than light can cross it. Eventually, all distant galaxies will vanish from our view, and our local group will merge into a single, aging galaxy adrift in an ever-cooling, ever-darkening void. This is the Big Freeze, a slow and lonely heat death, but there is a more violent alternative. What if dark energy is not constant? What if it grows stronger over time? In this scenario, the repulsive force would eventually overcome all other forces in the universe. Not just galaxy clusters would be torn apart, but individual galaxies, solar systems, planets, and even atoms themselves would be shredded in a final, catastrophic event known as the Big Rip. The very fabric of space-time would be torn asunder. The existence of dark energy raises a humbling question. Are we witnessing the first subtle signs of our universe's final dissolution? And why does the vacuum of nothingness possess such a dominant, explosive power? Even the most carefully planned journeys can hold unexpected surprises. As the Pioneer 10 and 11 spacecraft ventured beyond the outer planets, they carried with them a tiny, persistent mystery. Tracking data revealed that both probes were experiencing a minute, unexplained deceleration, a constant sunward tug so small it was equivalent to just 1/10,000,000th of the gravity we feel on Earth. For decades, this pioneer anomaly baffled scientists. Was it a flaw in our understanding of gravity itself? Could it be the gravitational pull of unseen, dark matter clustered in our solar system, or perhaps evidence of some other new physics? The anomaly became a constant, quiet hum in the background of deep space exploration, a puzzle that refused to be ignored. The solution, when it finally came, was not from the depths of interstellar space, but from a meticulous reconstruction of the spacecraft themselves. A team of scientists spent years recovering old telemetry data and analyzing the complex geometry of the probes. They realized the answer was heat. The plutonium in the spacecraft's power sources generated heat which was radiated away into space. But this radiation was not perfectly uniform. A tiny fraction more heat was being emitted from the back of the spacecraft, from the warm electronics compartments, than from the front. This anisotropic or directionally uneven thermal radiation acted like a soft, constant brake, providing just enough photon pressure to create the observed deceleration. The case of the Pioneer anomaly serves as a profound lesson in cosmic detective work. It highlights the incredible precision required to navigate the void and the subtle ways our own creations can mimic the whispers of new physics. It reminds us that before we can listen for the universe's deepest secrets, we must first learn to account for the sound of our own heartbeat in the machine. Even the faint afterglow of creation holds its own strange imperfections. Scattered across the map of the cosmic microwave background, the universe's first light is a patch of cold so large and so profound it defies easy explanation. This is the cold spot, a colossal region of space spanning nearly 2 billion light-years where the temperature of the ancient radiation is just a fraction lower than its surroundings. At first glance, such a variation might seem minor, but in the context of the Big Bang's echo, it is a staggering anomaly. The cold spot is not just a little bit cold, it is statistically improbable on a scale that challenges our standard model of cosmology. It is a cosmic bruise that should not exist, a blemish on the infant universe that has astronomers questioning the very fabric of reality. So what could have left such a mark? One leading theory suggests the cold spot is not a feature of the primordial universe at all, but a later development caused by a staggering emptiness. This idea points to the integrated Sachs-Wolf effect, a phenomenon where light loses energy as it travels through an expanding gravitational landscape. Imagine a photon, a particle of light from the Big Bang, falling into a gravitational well created by a massive galaxy cluster. It gains energy, appearing slightly hotter. As it climbs out, it loses that energy, but if the universe has expanded significantly during the photon's journey, the well becomes shallower and the photon cannot regain all the energy it lost. Now apply this to a truly vast region of nothingness, a supervoid of unimaginable scale. A photon entering this void would expend energy climbing out of the gravitational well of the surrounding dense matter. While traveling through the near-empty void, it would gain very little energy back. When it finally exits, the universe has expanded, and the well it must climb into is shallower. The photon arrives at our telescopes cooler and redder, creating the appearance of a cold spot. The problem is, to account for the cold spot, this void would need to be so immense that it pushes the limits of what we believe is structurally possible in the cosmos. We have found a large void in that general direction, but it is not nearly big enough to explain the temperature drop. The numbers simply do not add up, leaving the void theory as an incomplete answer. This failure has given weight to a far more speculative yet breathtaking possibility. Could the cold spot be the imprint of a collision with another universe? In the framework of the multiverse, our cosmos is just one bubble in a vast, frothing sea of space-time. If another bubble universe brushed against our own in the distant past, the energy of that collision could have drained away from a region of our nascent cosmos, leaving behind a cold, expanded scar. This cosmic bruise would be a fossilized record of contact with a reality entirely separate from our own. It is a hypothesis that stretches the boundaries of science, suggesting that the ultimate evidence for other universes is written not in the present, but in the faded light of the beginning. The cold spot forces us to confront a fundamental choice. Are we looking at a statistical fluke, a one-in-a-million cosmic coincidence that just happened to occur in our field of view? Or is this chill in the ancient light the first tangible evidence that our universe is not alone, but one of many in a grand and utterly alien multiverse? The answer lies frozen in the sky, a whisper from the dawn of time that speaks of either profound emptiness or a collision with another reality. The chill of the cosmic background radiation was soon followed by a visitor from a place far colder. In October 2017, a telescope in Hawaii spotted a tiny, fast-moving point of light that was already on its way out of our solar system. Named Oumuamua, Hawaiian for Scout, it was the first object ever detected that came from interstellar space. Its trajectory was a hyperbola, a path so extreme it proved this traveler was not bound by our sun's gravity, merely passing through on a journey from one star to another. The initial observations revealed a world of peculiarities. It exhibited no coma, the fuzzy envelope of gas and dust that typically surrounds a comet. It appeared as a bare, dark rock tumbling through the void, but the most profound mystery was its motion. As it sped away from the sun, something was giving it an extra push. Its acceleration could not be explained by gravity alone. Comets often get a speed boost from outgassing when ices on their surface heat up and vent jets of gas like a natural rocket engine. Yet Oumuamua showed no visible signs of this activity. No dust cloud, no gas tail, nothing. So what unseen force was propelling it? The scientific community fractured into camps, each proposing a solution. One group suggested it was a cosmic iceberg, a chunk of solid hydrogen. Such an object would vent hydrogen gas invisibly as it neared the sun, providing the necessary thrust without a visible coma. The problem is, a hydrogen iceberg is a fragile thing, unlikely to survive the long, radiation-filled journey between stars. Another idea posited that it was a dust bunny, an ultra-low-density fractal aggregate of material that could have been torn from a comet long ago. Its lightness would allow radiation pressure from the sun itself to push it along, accounting for the non-gravitational acceleration. Then came the most controversial hypothesis, one that captured the public imagination. Could Oumuamua be an artificial object, a piece of advanced alien technology? Astronomer Avi Loeb proposed that its acceleration profile and strange shape were consistent with a light sail. A light sail is a thin, reflective sheet that uses the gentle pressure of photons from a star to propel itself, much like a boat's sail catches the wind. If Oumuamua was a discarded light sail, perhaps from a derelict probe, its thin, pancake-like form would explain its dramatic brightness variations as it tumbled. We observed it brighten and dim by a factor of 10, suggesting an extremely elongated shape, perhaps 10 times longer than it was wide. A natural shard of rock would be unlikely to survive with such an extreme form. The debate raged not just about what Oumuamua was, but about how science should approach such anomalies. Was it more rational to exhaust every conceivable natural explanation, no matter how exotic, or to openly consider the remote possibility of an artificial origin? By the time we had turned our most powerful telescopes toward it, Oumuamua was already too far away and too faint to reveal more secrets. It faded into the darkness from whence it came, a silent messenger that left behind more questions than answers. Was it a strange new type of comet, a novel class of asteroid, or something else entirely? Its brief passage reminds us that the universe is capable of producing wonders we have not yet dreamed of, and that some mysteries are destined to remain forever sailing into the unknown. For decades, dark matter was the unseen architect behind every galaxy we could see. Its gravitational pull was the scaffolding that held the cosmos together, a necessary component for galaxies to even exist. Then astronomers found a ghost. A galaxy designated NGC 1052DF2 is a vast, diffuse collection of stars, so wispy and transparent you can literally see right through it to the galaxies beyond. When scientists measured the velocities of its star clusters, they expected to see the telltale signs of dark matter's hidden hand, the stars whipping around at speeds that betrayed the presence of an invisible mass. Instead, they found stillness. The star clusters were moving slowly, leisurely, at a pace that perfectly matched the gravitational pull of the galaxy's visible stars alone. There was no extra mass, no dark matter halo. They had found a galaxy that appeared to have none. This discovery sent a shockwave through the world of cosmology. A galaxy without dark matter should not be able to form, or at the very least, it should not be able to survive. The prevailing model suggests that in the early universe, dark matter condensed first into vast halos, and their gravity then drew in the normal gas that eventually formed stars. Without that dark matter seed, a galaxy like this one should be an impossibility. Its very existence forces us to question our most fundamental assumptions. How did this collection of stars come together without the cosmic glue that supposedly binds all galaxies? The debate over this ghostly galaxy has been fierce, centering on a critical detail: its distance from us. The calculation of its mass is entirely dependent on how far away we believe it is. One group of astronomers argues the original distance measurement was correct, confirming the dark matter deficit. Another team has proposed it is much closer to us. If that were true, the galaxy would be intrinsically smaller and less massive, and its slowly moving stars could once again be explained by the presence of a hefty dark matter halo. The most recent and precise measurements, however, continue to support the original, more distant location, strengthening the case for a truly dark matter-free galaxy. This leaves us with a profound and beautiful puzzle. Finding a galaxy with no dark matter is paradoxically some of the strongest evidence we have that dark matter is real. Why? Because it shatters a key alternative theory. If the anomalous motions in galaxies were caused by a modification to the laws of gravity, like MUND, then every single galaxy should behave according to those new rules. You cannot have a modified law of gravity that just stops working for one specific galaxy. The existence of NGC 1052DF2 suggests that dark matter is a real physical substance, one that can be separated from normal matter. It shows that dark matter is not inextricably linked to the stars we see. It is something that can be present or absent. This raises an even more intriguing question. If a galaxy can exist without its dark matter, what cosmic event could have stripped it away? Could it have been torn from its cradle in a violent collision with another galaxy, its dark matter stolen while the stars were left behind? We are left staring at a cosmic contradiction, a void within a void that challenges everything we thought we knew about the foundation of the universe. Far beyond the orbit of Neptune, our solar system does not simply fade into darkness. It holds a ring of frozen worlds known as the Kuiper Belt, a cosmic junkyard of icy debris left over from the planet's formation. Astronomers expected to find a vast, smoothly distributed population of these objects, gradually thinning out the farther you go from the Sun. But the belt does not end with a gentle fade. It stops abruptly. At a distance of about 50 astronomical units, the number of detected objects plummets. This is the Kuiper Cliff, a sudden and dramatic edge to our known planetary system that should not exist. It is as if you were walking through a forest that suddenly turns into an open, empty field with a perfectly straight border. The standard model of solar system formation cannot easily explain such a sharp boundary. If the disk of primordial material just ran out, the drop-off should be gradual, not a sheer wall. So what carved this edge into the frozen depths of space? The most tantalizing theory points to the gravitational hand of an unseen giant. A hypothetical planet, often called Planet 9, could be orbiting far beyond the cliff. The immense gravity of such a world would act as a shepherd, clearing out a vast swath of space. Its distant, slow orbit could have gravitationally stirred up the region over billions of years, ejecting countless objects into interstellar space or throwing them into orbits that never bring them close enough for us to detect. The Kuiper Cliff would then be the ghostly imprint of this hidden planet, a gravitational signature written in the absence of ice. Yet finding this world is a monumental challenge. It would be incredibly faint, moving at a snail's pace across the sky, and its predicted orbit is so vast that a single year on Planet 9 could last 20,000 Earth years. Another possibility reaches back to the solar system's violent infancy. Perhaps the protoplanetary disk from which all the planets formed truly did have a sharp outer edge, a cut-off point created by the gravitational influence of a passing star in our Sun's birth cluster. This stellar flyby billions of years ago could have stripped away the outer material, leaving behind a pre-formed cliff that the Kuiper Belt simply inherited. Or maybe the early Sun formed in a region of space rich in massive, bright stars whose intense radiation evaporated the lighter ices in the outer disk, preventing large objects from coalescing beyond a certain point. Each theory has its own compelling narrative, but the cliff remains. It stands as a silent challenge, a boundary in our own cosmic backyard that hints at either a missing world or a forgotten chapter from our sun's earliest days. What will we find when we finally peer over this edge? Is it the gravitational domain of a true ninth planet, or the fossilized edge of a lost stellar nursery? Even the faintest whisper from the beginning of time can unsettle our deepest assumptions. As we map the cosmic microwave background, the universe's ancient afterglow, we expect to see a random tapestry of hot and cold spots, a frozen record of the primordial chaos from which everything was born. This expectation is rooted in the cosmological principle, a cornerstone of modern cosmology that states the universe is homogeneous and isotropic. In simpler terms, the universe should look the same in all directions, with no preferred location and no special axis. But a strange pattern emerged, one so cosmologically troubling it was given a provocative name, the axis of evil. This is not a physical structure, but a controversial statistical alignment. The largest fluctuations in the background radiation, the biggest hot and cold spots, appear to be mysteriously oriented with the plane of our own solar system. It is as if the echo of the Big Bang is subtly aware of our local cosmic neighborhood, a correlation that should be astronomically impossible. Why is this so deeply unsettling? Because it suggests a preferred direction in the cosmos, a cosmic north that aligns with our own backyard. This directly violates the cosmological principle, which insists that we do not occupy a special place in the universe. If the axis of evil is real, it implies that our position is not random, but somehow linked to the largest scale structure of reality itself. It would be like discovering that the pattern of the first light ever emitted is subtly synchronized with the orbit of Earth around the Sun. Scientists have been grappling with this anomaly for years, questioning whether they are seeing a true physical effect or a profound statistical fluke. The primary challenge is ruling out contamination from our own galaxy. The Milky Way's foreground emissions from dust and charged particles could potentially be imprinting this pattern onto the data. Teams have meticulously subtracted these foregrounds using different methods, yet the strange alignment persists. Others have performed exhaustive statistical tests, simulating universes to see how often such an alignment might appear by pure chance. The results remain inconclusive, hovering on the edge of statistical significance. Some analyses suggest the probability of this happening randomly is less than 1 in 1,000, while others argue that when you account for the fact that we are looking for any unusual pattern, the odds are not so remote. This alignment forces us to confront a difficult choice. Do we need to revise one of the most fundamental tenets of cosmology, the idea that the universe has no center and no edge? Or are we simply seeing a grand cosmic mirage, a trick of perspective that will vanish with more precise data? The axis of evil stands as a profound reminder that our most basic assumptions about reality are always subject to revision by the next unexpected whisper from the void. Orbiting silently above us is a legend woven from shadow and misinterpretation. The story of the Black Knight satellite tells of an ancient alien probe that has been circling our planet for thousands of years, a silent sentinel watching over humanity. This myth grew from a tapestry of strange events, beginning with signals. In the late 19th century, Nikola Tesla reported receiving a peculiar, repeating radio signal he believed could be of extraterrestrial origin. Decades later, in the 1920s, amateur radio operators began picking up strange echoes, delayed versions of their own transmissions that seemed to bounce off something unknown in orbit. The most famous chapter came in 1960 when a radar operator tracked an unknown object in a polar orbit, a path that was considered unusual for the time. Newspaper articles dubbed it the Black Knight, and a legend was born. The mystery was amplified by a photograph. During a 1998 space shuttle mission, an image was taken that appeared to show a strange, dark, geometric object against the backdrop of Earth. It looked artificial, alien, and perfectly fit the description of the legendary satellite. So what was this object that has fueled so much speculation? The truth, as is often the case, is more mundane but no less fascinating. The vast majority of sightings, including the famous shuttle photograph, have been identified as human-made space debris. The shuttle image almost certainly captured a thermal blanket that had been lost during an earlier spacewalk, a piece of insulation tumbling end over end in the void. The strange radar contacts were likely bits of discarded hardware or the upper stage of a rocket. As for the unusual polar orbit, it is now a standard trajectory for many of our own scientific satellites. The radio signals and echoes have explanations rooted in natural phenomena, from solar flares creating radio noise to the ionosphere bouncing long-delayed signals back to Earth. Yet the story of the Black Knight persists with a power that defies simple debunking. It taps into a deep-seated human desire for connection, for the idea that we are not alone and that our history is far grander than we know. The myth offers a thrilling narrative, a secret history hidden in plain sight above our heads. It is a modern folktale, a cosmic ghost story passed down through decades. Why does this particular piece of space junk hold such a powerful grip on our imagination? Perhaps because the reality of a lost thermal blanket is so disappointingly ordinary when compared to the grandeur of an interstellar artifact. The void of space is vast and silent, and we long to find evidence that someone else is out there, that we have been visited. The Black Knight is a testament to that longing, a cultural artifact born from our own hopes and projected onto the endless dark. It reminds us that sometimes the greatest mysteries are not what lies in the cosmos, but the stories we choose to believe. While we spin stories of satellites in Earth's orbit, a genuine geometric marvel spins in the depths of our solar system. At Saturn's North Pole, a storm of unimaginable scale rages, but it is not a chaotic swirl. It is a perfect, persistent hexagon, a six-sided cloud pattern so vast it could engulf 4 Earths. This is not an artist's rendering or a trick of the light. It is a real, stable structure, a colossal hurricane with geometrically straight walls, and it is unlike anything else we have ever seen on any other planet. The Voyager probes first glimpsed it in the 1980s, but it was the Cassini spacecraft that gave us our first truly detailed look. Orbiting Saturn for over a decade, Cassini revealed the hexagon in all its breathtaking glory, showing it was not a transient feature but a permanent fixture of the planet's atmosphere, towering hundreds of kilometers high and rotating with a clockwork precision. How can a fluid, chaotic system like a planetary atmosphere create and maintain something so perfectly angular? The answer lies not in solid architecture, but in the physics of spinning fluids. To understand it, scientists have turned to laboratory experiments, filling large cylinders with water and spinning them to simulate planetary conditions. When the rotation speed and the flow of the fluid are just right, something remarkable happens. Instabilities at the boundary between different flow speeds can generate standing waves, creating stable polygonal shapes within the swirling liquid. In these tanks, they have successfully created everything from 3-sided triangles to an 8-sided octagon. The hexagon is simply the shape that emerges most readily under conditions that mirror Saturn's polar jet stream. The leading theory suggests that a powerful, eastward-flowing jet stream at Saturn's North Pole acts as a waveguide. A disturbance, perhaps from a smaller storm or an irregularity deep within the planet, created a standing wave that became locked into this fast-moving river of air. The physics is similar to what you might see when you vibrate a plate of water, creating stable patterns on its surface. On Saturn, the planet's rapid rotation and the specific wind speeds conspire to trap this wave, preventing it from dissipating or changing shape. The hexagon is essentially a self-perpetuating atmospheric echo, a vibration frozen in time and scaled up to planetary proportions. It is a natural resonance, a note played on the atmosphere of a giant that has been holding its pitch for decades and likely much longer. This stunning structure forces us to reconsider what is possible in nature's workshop. It demonstrates that perfect geometry can emerge from pure chaos, a six-sided signature written in clouds and wind, forever circling the pole of a distant world. Even the most chaotic deaths of stars can produce stunning order. In the constellation Monoceros, a celestial structure defies all expectations of cosmic form. The Red Rectangle Nebula is precisely what its name suggests, a vast geometric cloud of glowing gas that appears as a near-perfect three-dimensional box in the void. At its heart lies not one but two aging stars locked in a tight orbital dance. Their final act is creating one of the most symmetrical and bizarre objects in our galaxy. This is not the ragged, expanding shell of a typical planetary nebula. Instead, twin jets of gas erupt from the poles of the primary star, funneled and shaped by a thick, dense disk of dust that encircles both stars like a cosmic donut. This dust torus acts as a nozzle, squeezing the outflowing material into two opposing cones. From our vantage point on Earth, we are looking directly down the barrel of this structure. The edges of these cones, illuminated by the central stars, form the sharp, almost ruler straight sides of the rectangle we see. The concentric rings that give the nebula its layered appearance are thought to be pulses, a series of hiccups in the mass lost from the dying star over thousands of years. Each ring marks an earlier eruption, a fossilized record of the star's final, unstable centuries. This makes the Red Rectangle a unique cosmic laboratory. Here, we can study the precise mechanics of how binary stars interact as they die, and how their combined gravitational and radiative forces can sculpt chaos into perfect geometry. The presence of unusual hydrocarbons in the nebula's dust also provides clues to the complex chemistry that occurs around aging stars, chemistry that might seed future planetary systems with the building blocks of life. Why has this system created such a perfect form when others explode into random, beautiful clouds? The answer seems to lie in the delicate balance of its components, a specific set of conditions that turns a stellar death rattle into a work of cosmic art. It stands as a breathtaking reminder that the universe has a hidden preference for pattern, a tendency toward order that can emerge from the most turbulent of processes. What other symmetrical wonders are waiting to be discovered in the final breaths of other suns? Our own galaxy is a cosmic predator, silently consuming its smaller neighbors in a process as ancient as the universe itself. Galactic cannibalism is the slow, gravitational destruction of a dwarf galaxy by a larger one, a feast that takes billions of years to complete. The Milky Way is no peaceful island universe. It is a monster with a voracious appetite, and we can see the evidence of its past meals scattered across our sky. Right now, it is in the process of tearing apart the Sagittarius dwarf spheroidal galaxy. This tiny satellite galaxy has orbited our own for eons, and with each pass, the Milky Way's immense gravity pulls it apart, stretching its stars into long, shimmering rivers that wrap around us. These are stellar streams, the ghosts of galaxies past, and they tell the story of our galaxy's violent growth. In the distant future, this cycle of consumption will reach a spectacular climax. The Andromeda Galaxy, our largest galactic neighbor, is hurtling toward the Milky Way at 250,000 miles per hour. In about 4.5 billion years, we will collide. This will not be a fiery crash of stars, for space is too vast and empty for that. Instead, it will be a slow, gravitational dance of destruction. The two galaxies will pass through each other, their gravity violently distorting their majestic spiral arms, pulling out long tails of stars and gas. They will separate, then fall back together, merging over countless millions of years into a single, giant elliptical galaxy, which astronomers have already nicknamed Milkomda. This is the ultimate form of galactic cannibalism, a cosmic feast where both diners are forever changed. The stellar streams left behind from these events are more than just debris. They are the archaeological records of a galaxy's history. By mapping the motions and compositions of stars in these streams, astronomers can rewind the clock. They can determine when a dwarf galaxy was captured, how many times it orbited, and even what it was made of, piecing together the family tree of our galactic home. These faint trails of stars are the fossils of the cosmos, revealing that even the grandest structures are built from countless acts of silent, gravitational violence. What other stories of ancient feasts are written in the faint starlight we have yet to decipher? Amidst the chaos of galactic collisions, one structure stands out for its serene and perfect geometry. Hoag's object is a galaxy that defies the typical spiral or elliptical forms, appearing instead as a stunning cosmic bullseye. A nearly perfect ring of young, hot blue stars encircles a core of much older yellow stars with a dark, seemingly empty gap separating the two. It is a celestial donut of staggering proportions and beauty, a configuration so rare it feels almost impossible. The central core is a dense, spherical hub typical of an elliptical galaxy, while the outer ring is a vibrant nursery of star formation, a brilliant blue circle of newborn suns. The profound mystery is what connects them, or rather, what does not. That dark gap is a region largely devoid of the stars that should logically bridge the core and the ring, a void that challenges our understanding of galactic evolution. How did such a perfectly balanced structure come to be? The leading theory points to a violent past, a galactic collision billions of years ago. In this scenario, a smaller galaxy might have plunged straight through the heart of a larger disk galaxy. The gravitational shockwave from this cosmic bullseye would have rippled outward, compressing gas and triggering a wave of star formation in a perfect circle, while the central region settled back into a calm, aging hub. The intruder galaxy itself would have been torn apart and absorbed, leaving no trace behind except for the beautiful ring it created. An alternative idea suggests the ring formed from an internal instability, a resonant bar structure that later dissolved, leaving only this rippling circle of stars. The true origin remains one of astronomy's most captivating puzzles. Yet, the wonder of Hoag's object deepens with an almost unbelievable detail. Peering through the dark gap between the ring and the core, astronomers have spotted another, much more distant ring galaxy, a perfect smaller bullseye shining from the far depths of the universe. This incredible alignment is a one-in-a-million cosmic coincidence, a photograph that captures two separate ring galaxies in a single frame, one nestled within the emptiness of the other. It is a breathtaking glimpse of a pattern that repeats across the cosmos, a reminder that even in the vast and random universe, moments of perfect, inexplicable harmony can emerge from the dark. A cosmic behemoth is on the run. Astronomers have spotted a supermassive black hole, a monster weighing as much as 20 million suns, hurtling through the darkness at a staggering speed. It is not drifting quietly through the void, but blazing a trail of creation, leaving a 200,000 light-year long river of newborn stars in its wake. This is not the behavior of a quiet gravitational anchor, but of a cosmic cannonball shot from a galactic catastrophe. The most compelling explanation for this incredible flight involves a gravitational slingshot of epic proportions. Imagine a system of three supermassive black holes, the dense hearts of three merging galaxies, locked in a chaotic dance. Their orbits become unstable, a gravitational tug of war with no winners. In this cosmic fray, two of the black holes can pair up, tightening their orbit and stealing energy from the third. This transfer acts like a catapult, violently flinging the lone black hole clear out of its host galaxy and into the intergalactic wilderness. The ejected black hole is moving so fast it would travel from Earth to the Moon in just 14 minutes. As it plows through the dense gas clouds that linger between galaxies, its immense gravity compresses the material, not to feed itself but to trigger the birth of new suns. The wake of young, blue stars is not a trail of destruction but a ribbon of creation, a stellar nursery forged in the shockwave of the black hole's passage. This bizarre phenomenon provides a startling new perspective on how galaxies evolve. We have long suspected that galactic mergers fling stars into the halos of galaxies, but the ejection of the central supermassive black hole itself was a theoretical possibility never before caught in the act. Its existence suggests that some galaxies may be left as wandering, leaderless ships, their central gravitational engine ripped away. What happens to a galaxy that loses its heart? Does it slowly drift apart, or does a new black hole eventually form to take its place? This runaway giant and its starlit trail are a living laboratory, a chance to witness the most violent and transformative events in the universe and understand the powerful forces that sculpt the cosmic landscape. The mystery of Tabby's star has deepened with time, not with a single dramatic answer, but through the slow, meticulous work of scientific observation. Years of intense monitoring finally paid off when astronomers caught the star in the act of one of its major dimming events, and they trained a full arsenal of telescopes on it. The data revealed a crucial clue hidden within the colors of the dimmed light. When the star faded, it dimmed more significantly in blue light than in red light. This simple fact was a death knell for the alien megastructure theory. A solid object like a planet or a vast solar panel would block all wavelengths of light equally, creating a uniform dimming across the spectrum. The observed effect, however, pointed directly to something much smaller than a grain of sand, dust. Tiny dust particles are excellent at scattering blue light, the same reason our sky appears blue while allowing more red light to pass through. The star was being obscured by a vast, uneven cloud of cosmic dust, not a solid megastructure. Further analysis showed this dust is not distributed in a neat, spherical shell around the star. Instead, it is clumped together in asymmetric, dynamic clouds, which explains the bizarre, irregular pattern of the dimming. One leading theory suggests that the dust is the debris from a shattered moon or a catastrophic planetary collision, creating a chaotic swarm of material on a highly elliptical orbit. As this cloud of fragments swings close to the star, it blocks our view, creating the dramatic dips in brightness. The scientific journey surrounding Tabby's star is a powerful lesson in how we explore the cosmos. An extraordinary claim sparked global interest and rigorous investigation, driving technology and collaboration forward. The initial, thrilling hypothesis of alien engineering forced us to look closer and gather better data, which ultimately led us back to a natural, if still extraordinary, explanation. We are left not with disappointment, but with a renewed sense of wonder at the sheer variety of planetary systems. What kind of violent event could have created such an immense and ragged dust cloud? And what does that tell us about the turbulent history of this strange star? Some galaxies are so faint they are almost invisible, cosmic ghosts that drift through the void. These are the ultra-diffuse galaxies, immense structures that stretch as wide as our own Milky Way but contain a mere 1% of its stars. Imagine a metropolis the size of New York City, but with only a handful of streetlights to illuminate the entire urban sprawl. That is the profound emptiness of a galaxy like Dragonfly 44. For every star we have in our vibrant spiral, Dragonfly 44 has a vast dark gulf. These galaxies are so ethereal that they were only discovered when our telescopes became powerful enough to see through their ghostly forms, spotting them as faint smudges against the deeper black. Their existence alone is a puzzle. How does a structure so large and so diffuse, with so little gravitational glue from visible stars, manage to hold itself together without simply flying apart? The answer, it seems, is not the same for all of them, and that is where the true mystery lies. Some of these fluffy giants are incredibly rich in dark matter. Their rotations are so fast that without the gravitational anchor of an immense, unseen dark matter halo, they would have disintegrated eons ago. They are essentially vast, bloated halos of dark matter that, for reasons we do not understand, failed to form many stars. They are all invisible scaffolding with almost no visible building, yet other ultra-diffuse galaxies present the opposite problem. They appear to have little or no dark matter at all. This contradiction is a profound challenge to our models of galaxy formation. We thought we understood the recipe. First, a halo of dark matter condenses, and then gas is drawn in to form stars. But these galaxies break that mold. How can you have two galaxies of the same immense size and the same stunning faintness, yet one is dominated by dark matter and the other is virtually empty of it? It suggests that the path to becoming a galaxy is far more diverse and chaotic than we ever imagined. Perhaps the dark matter-rich ones are failed giants, whose gas was stripped away early by cosmic tides, preventing stars from ever lighting up in great numbers. The ones without dark matter might be the battered remnants of larger galaxies, their stars and dark matter torn asunder in violent encounters, leaving behind only the most loosely bound stars to form a ghostly echo. Each of these faint smudges on our telescopes is a question about the fundamental forces that build our universe. Why do some dark matter halos remain dark while others are completely lost? The search for these cosmic phantoms continues, forcing us to question if we have been seeing only the brightest tip of the galactic iceberg all along. Some stars do not simply burn, they rage. Luminous blue variables are the universe's most volatile and colossal stellar giants, immense hypergiants that exist in a perpetual state of violent instability. These are stars living on the very edge of catastrophe, so massive and luminous that their own gravity can barely contain them. They periodically shudder and convulse, expelling vast shells of their own mass into the surrounding void in eruptions of unimaginable power. They are stellar behemoths teetering on the brink of becoming supernova, and their dramatic outbursts offer us a rare glimpse into the final, frantic chapters in the lives of the most massive stars in the cosmos. The most famous of these celestial titans is Eta Carinae, a binary star system that put on a spectacular show for 19th century astronomers. In the 1840s, it underwent what is now called the Great Eruption, violently ejecting the equivalent of at least 10 times the mass of our entire Sun into space. For over a decade, this single star became the second brightest object in the entire night sky, outshone only by Sirius. This was not a quiet fading, but a stellar temper tantrum of epic proportions. The explosion was so powerful it created the homunculus nebula, a vast bipolar cloud of gas and dust that still expands outward from the star today, a beautiful and permanent scar from its near self-destruction. Why would a star behave in such an erratic and self-destructive manner? The core of a luminous blue variable is a raging inferno, and the radiation pressure pushing outward from within becomes so intense that it nearly overcomes the inward pull of gravity. The star becomes bloated and unstable, reaching a point where its outer layers are no longer firmly bound. It is like a pot of water boiling over, with the star's own light literally pushing its atmosphere into space. These outbursts are a star's way of shedding immense weight before its final, inevitable collapse into a supernova. Studying these erratic giants is crucial because they represent a fleeting, violent phase that only the most massive stars experience. They are the missing link between stable, long-lived blue supergiants and their ultimate fate as brilliant supernova or even gamma-ray bursts. By observing their death throes, we learn about the processes that seed galaxies with heavy elements and the conditions that lead to the formation of the universe's most exotic objects like stellar mass black holes. Eta Carinae is a ticking time bomb, and its next great eruption could be its last. When it finally goes supernova, it will be a spectacular event, potentially visible even in our daytime sky. What will we learn from the final, cataclysmic death of this unstable giant, and how many more of these volatile stars are lurking in the darkness, waiting for their moment to explode? Our journey through the galaxy may hold the key to our planet's most catastrophic past. As our solar system travels around the Milky Way, it does not move on a flat, stable plane. Instead, it bobs up and down, oscillating vertically through the galactic disk in a cycle that takes roughly 60 million years to complete. This grand cosmic rhythm, known as the galactic year, coincides with a startling pattern found in Earth's own geological record. Analysis of the fossil record reveals that mass extinction events, where a significant percentage of all life on Earth vanishes, appear to occur with a similar periodicity, approximately every 30 million years. This correlation is one of the most provocative ideas in astrobiology, suggesting that the fate of life on our world may be written in the stars. The proposed mechanisms for this cosmic connection are as dramatic as the extinctions themselves. One leading theory points to the Oort cloud, that vast, icy reservoir of comets at the outermost edge of our solar system. As the Sun oscillates upward and downward, it passes through the densest part of the galactic plane, a region crowded with stars, gas clouds, and dark matter. The gravitational tug from this extra mass could disturb the delicate orbital dance of countless comets, sending a shower of icy bodies plunging toward the inner solar system. This would dramatically increase the chance of a catastrophic impact, much like the one that ended the reign of the dinosaurs. Another possibility involves cosmic radiation. When our solar system is far from the galactic plane, we are somewhat shielded by the Milky Way's magnetic fields. But as we pass through the crowded midplane, that protection weakens, potentially exposing Earth to higher levels of destructive radiation from interstellar space. This could damage the planet's ozone layer, allowing harmful ultraviolet radiation from our own sun to reach the surface, triggering climate shifts and collapsing ecosystems. The debate over this hypothesis is fierce. Skeptics argue that the geological record is incomplete, and that the apparent pattern could be a statistical fluke, a coincidence stretched across hundreds of millions of years. Proponents counter with increasingly precise data, showing that the timing of these extinction events aligns too well with our galactic motion to be easily dismissed. Could it be that the rise and fall of Earth's dominant species is choreographed by the slow, silent dance of our sun around the galaxy? This idea forces us to see our planet not as an isolated world, but as an integral part of a dynamic and sometimes dangerous cosmic environment. The very motion that carries us through the Milky Way might also be the clock that ticks toward life's greatest challenges. A fleeting whisper from a nearby star once promised a cosmic conversation. In August 2016, the Ratan 600 radio telescope in Russia detected a powerful signal originating from the star HD 164595, a sun-like star just 95 light-years away. This was not a random burst of static, but a strong, narrowband radio signal, precisely the kind of signature scientists predict an advanced civilization might use for interstellar communication. The news sent a ripple of excitement through the small community of astronomers dedicated to the search for extraterrestrial intelligence. For a brief, tantalizing moment, it seemed we might have received our first deliberate hello. The signal's characteristics were what made it so compelling. Its intensity suggested a source of immense power, far beyond what we could produce, or it implied a transmitter deliberately aimed in our direction, a cosmic lighthouse beam sweeping past Earth. The star itself was an ideal candidate, a near twin to our own sun, raising the possibility of a stable, Earth-like planet orbiting within its habitable zone. The discovery triggered an immediate and coordinated response. Telescopes across the globe, including the powerful Allen Telescope Array in California, swiftly turned their dishes toward HD 164595, listening intently for a repeat of the signal, for any confirmation that this was more than a celestial fluke. They heard only silence. The follow-up observations found nothing, no repeating pattern, no secondary signal, no trace of the anomaly. The initial burst of excitement was met with the cold, hard reality of empty data. The investigation then turned inward to our own crowded sky. The rigorous process of elimination began, a necessary chore in the modern search for intelligence. Scientists meticulously cross-referenced the signal's properties with known human activity. The conclusion was both definitive and disappointing. The signal's frequency and its movement across the sky pointed not to a distant star, but to a much closer source, a passing military satellite. This human-made object, likely on a secretive mission, had inadvertently mimicked the very signature we are searching for, its radio emissions bouncing off the telescope's dish and creating a perfect cosmic false alarm. The story of the signal from HD 164595 is a testament to the painstaking diligence required in this field. It highlights the immense challenge of listening for a faint whisper of hello in a cacophony of our own making. Every unusual blip must be scrutinized. Every potential candidate must survive the gauntlet of terrestrial explanation. This event was not a failure, but a demonstration of the scientific method at work, a process that separates hopeful speculation from verifiable fact. It reminds us that the path to a monumental discovery is paved with disciplined skepticism, and that the greatest challenge in finding another civilization may first be learning to recognize the sound of our own. Silence can be as profound as any signal. Orbiting a dim, cool red dwarf star just 40 light-years away is the TRAPPIST-1 system, a compact family of 7 rocky worlds, 3 of which are nestled perfectly within the star's habitable zone where temperatures could allow for liquid water. This discovery was met with immense excitement as it presented our best candidate yet for a nearby stellar neighborhood teeming with possibilities. Here was a system packed with Earth-sized planets, a seemingly ideal setup for life to arise, perhaps even flourish. Yet when we turned our most sensitive instruments toward this promising target, we were met with a deep and puzzling quiet. No artificial radio transmissions, no laser pulses, no technosignatures of any kind leak from this planetary collective. The system, for all its potential, appears utterly silent. This absence of noise is itself a powerful piece of data, forcing us to reconsider the conditions necessary for intelligent life to not only emerge but to persist and make its presence known. Red dwarf stars like TRAPPIST-1 are notoriously tempestuous. They are prone to violent flares and eruptions of ultraviolet radiation that can strip away the atmospheres of orbiting planets and bathe their surfaces in sterilizing radiation. For life to survive in such an environment, a planet would need a robust magnetic field and a thick atmosphere for protection, or life would need to exist in sheltered subterranean or oceanic environments. The silence we observe could mean that these worlds, while the right size and distance, are barren wastelands, their surfaces scoured clean by their star's youthful fury. Alternatively, the quiet could hint at a more subtle truth. Perhaps life did emerge in the TRAPPIST-1 system, but it never developed the technology for interstellar communication, remaining at a microbial or animal level. Or maybe an advanced civilization did arise, but it has chosen to remain silent, or it communicates in ways we have not yet learned to detect. Our searches are like listening for a specific whisper in a hurricane, and we may simply be tuning our instruments to the wrong frequency or the wrong time. The star's planets are likely tidally locked, with one face in permanent daylight and the other in endless night. A civilization might flourish in the narrow twilight zone between these extremes, its signals beamed in a direction we never see. The great silence from such a promising system is a humbling reminder that a habitable zone is not a guarantee of an inhabited world, and that the universe holds its secrets closely, even when they are right on our cosmic doorstep. The quiet of the TRAPPIST-1 system stands in stark contrast to the furious brilliance of the infant universe. Billions of years ago, when the cosmos was a mere toddler, it already hosted monsters. We now find quasars, the dazzlingly bright cores of ancient galaxies, shining from an era when the universe was less than 1 billion years old. These are not just any active galaxies, they are powered by supermassive black holes weighing billions of times more than our Sun. Their existence is a profound cosmological crisis. According to our best models of black hole formation, There simply has not been enough time for such behemoths to grow. A black hole forms from the collapse of a massive star, creating a seed of perhaps a few dozen solar masses. It then grows by slowly accreting gas and merging with other black holes. This process is governed by the Eddington limit, a kind of cosmic speed limit for growth where the intense radiation from the infalling material actually pushes back, preventing it from feeding too quickly. To reach 1 billion solar masses in under 1 billion years, these primordial black holes would have had to break this rule consistently, feasting at a breakneck pace from the very beginning. The numbers simply do not add up. It is like finding a fully grown ancient redwood tree sprouting from a crack in the pavement just a year after the concrete was poured. How did the seeds for these cosmic giants form so quickly, and how did they grow so impossibly fast? This overmassive black hole problem forces astronomers to consider radical alternatives. One leading idea is the direct collapse black hole. In this scenario, immense clouds of pristine gas in the early universe before the first stars had fully formed could have collapsed directly under their own weight. They would have skipped the entire star-forming stage entirely, plummeting straight into a massive black hole seed thousands of times more massive than the Sun. With such a colossal head start, these seeds could then accrete matter at a more reasonable pace and still become the supermassive giants we observe. Another, even more exotic possibility reaches back to the first fleeting moments after the Big Bang. Intense density fluctuations in the newborn cosmos could have created primordial black holes. These would not be born from dying stars, but from the raw, searing energy of creation itself. They could have been forged with a wide range of sizes, from microscopic to supermassive, providing the ready-made seeds that modern galaxies were built upon. The hunt is now on to find the missing links, the intermediate-sized black holes that could prove one of these theories correct. Each newly discovered ancient quasar pushes the problem further back in time, tightening the constraints on our models. What does it mean that the universe was able to build its most massive structures almost immediately? Were the conditions of the infant cosmos far wilder and more fertile than we ever dreamed? Or are we missing a fundamental chapter in the story of how gravity shapes the universe? Perhaps the Great Silence is a symptom of success, not failure. In the mid-20th century, a scientist named John Calhoun created a utopia for mice. He called it Universe 25, a perfect environment with unlimited food, water, and nesting material, safe from predators and disease. The population exploded at first, but then something strange happened. Social bonds frayed, mice became listless and withdrawn, obsessed with grooming but incapable of forming normal relationships. They lost interest in mating, and violence became common. Despite the abundance, the entire colony collapsed into extinction, a victim of its own perfect world. This behavioral sink offers a chilling metaphor for one potential answer to the Fermi Paradox. What if the Great Filter is not a cosmic catastrophe, but a societal one? An advanced civilization, having mastered its environment and conquered scarcity, might face a different kind of threat, a psychological and social decay born from a lack of challenge. In a world where every need is met by technology, where virtual realities are more compelling than physical exploration, what drives a society to reach for the stars? The immense effort and resources required for interstellar travel might seem pointless to a population lost in technological ennui. The universe next door could be filled with the digital ghosts of civilizations that chose to turn inward, to live in curated simulations rather than confront the vast, empty silence of real space. They would leave no radio signals because they are no longer talking to anyone, not even themselves. Their final act would not be a bang but a whimper, a slow fading into self-absorption. Or perhaps the collapse is more active. The same technological prowess that could build starships might also create unprecedented social stratification or weaponize apathy. A civilization could fracture, its collective will shattered by internal conflicts or a simple loss of purpose, long before it ever assembles its first interstellar probe. The silence we hear may not be the silence of emptiness, but the quiet of a million worlds that have already finished their conversations, having found all the answers they ever wanted within the comfortable confines of their own creation. Is the ultimate challenge for any intelligent species not to survive its infancy, but to find a reason to leave its cradle once it has grown up. Even our newest and most powerful eye on the cosmos is revealing a universe far stranger than we dreamed. The James Webb Space Telescope was built to see the first galaxies being born, to witness the universe's infancy. Instead, it found giants in the deepest, oldest reaches of space, corresponding to a time when the cosmos was only a few 100 million years old. Webb has spotted galaxies that are impossibly massive and mature. These are not the faint, chaotic blobs of nascent stars we expected. They are fully formed, colossal structures, shining with the light of hundreds of billions of suns, galaxies that by our current models should not have had nearly enough time to assemble. It is like finding a sprawling, ancient city in the archaeological layer of a simple hunter-gatherer camp. These discoveries are forcing a profound and urgent rewrite of cosmology's foundational story. How could so much structure form so quickly after the Big Bang? The gentle, gradual tug of gravity working on the dark matter scaffolding we thought we understood seems too slow, too inefficient to build such titans in a cosmic blink. The timeline of galaxy formation appears wildly off, suggesting that the early universe was a far more dynamic and fertile place than our theories allowed. Some scientists are now questioning the very nature of dark matter itself. Perhaps it is not the cold, slow-moving substance we have long presumed. Could it be warm or even interact with itself in ways that allowed it to clump together and form gravitational seeds with breathtaking speed? Or does the answer lie in the voracious appetites of the first supermassive black holes, which might have grown at impossible rates, their gravity pulling in vast clouds of gas to form stars in a furious whirlwind of creation? Each new image from Webb is not just a pretty picture, it is a direct challenge to our understanding of cosmic evolution. The telescope was designed to answer our oldest questions, but its greatest gift may be the new, deeper mysteries it unveils. It shows us that the universe, even in its first chapters, was capable of engineering on a scale and with a speed that we are only beginning to comprehend. What other foundational truths will we be forced to reconsider as we continue to stare back into the dawn of time? From the immense pull of the Great Attractor to the fleeting brilliance of fast radio bursts, our journey through these 30 cosmic riddles reveals a universe that is anything but settled. We have seen galaxies racing toward unseen horizons, stars flickering under the veil of strange dust, and the very fabric of space stretching under the influence of a mysterious dark energy. We have encountered voids of profound nothingness and structures of impossible geometry. Each of these phenomena is a question mark written across the cosmos, a challenge to our understanding of physics and reality itself. These are not failures of science, but its very lifeblood. Every anomaly, every baffling observation is a beacon guiding us toward a deeper truth. They force us to build better telescopes, to dream up new theories, and to push the boundaries of human knowledge. The universe does not give up its secrets easily, and it is in the struggle to comprehend the incomprehensible that we make our greatest leaps. So the next time you find yourself under a clear night sky, remember that you are not just looking at a static tapestry of lights. You are gazing upon a living, breathing mystery, a cosmic frontier filled with whispers of dark matter, the echoes of ancient collisions, and the possibility of realities beyond our own. The greatest discoveries are still waiting, hidden in the dark. We want to know which of these cosmic puzzles captured your imagination the most. Share your thoughts in the comments below and keep looking.